Hello and welcome back to High Peak Education. I would like to perform a calculation now which is going to show us how linear kinetic energy and rotational kinetic energy are really one and the same thing. Energy, we recall, is a scalar, so it is independent of direction. And since it is independent of direction, I want you to realize that when we consider these balls, we can look at their linear kinetic energy and add all of those up, or we can look at their rotational kinetic energy and add that all up, and we should get the same number because energy is, again, a scalar quantity. So let's read this problem. Rigid rods of negligible mass lying along the y-axis connect three particles. The system rotates about the x-axis with an angular speed of 2.0 radians per second. Find A, the moment of inertia about the x-axis and the total rotational kinetic energy. B, the tangential speed of each particle and the total kinetic energy. So in the first case, we should calculate the rotational way. In the second case, we should calculate the linear way. So let's get started. So for part A, we first want the moment of inertia. Now, by the way, I recommend we should label these masses. Let's call this mass 1. And let's call this mass 2, and let's call this mass 3. So the masses are labeled there in terms of their masses, and we should think about their radii. Now a radius is a positive value that extends from the origin, and even if you don't like that, note that when we take a radius squared, any non-zero number squared is positive. So I would suggest to you that radius 1 is equal to 3.00 meters. Radius 2 is equal to positive 2.00 meters. And then finally, radius 3 is equal to positive 4.00 meters. And that's because this will be the axis of rotation, this x-axis. So this right here is the point that this y-axis will pivot around. Okay, so that means the total rotational inertia will be m1 r1 squared plus m2 r2 squared plus m3 r3 squared. Notice that we're using the formula mr squared, which is the rotational inertia formula for a point mass, and we're just making it specific to each of these masses. So let us insert each of the numbers. That's 4.00 kilograms multiplied by its radius of 3.00 meters, and we square that, plus the mass 2, and that's 2.00 kilograms, times its radius of 2.00 meters, and we square that. And then we do plus, the last mass is 3.00 kilograms times the radius of 4.00 meters. And we square that. So let's go ahead and get this total rotational inertia. So looking at the calculator, let's calculate this. 4 times 3 squared plus 2 times 2 squared plus 3 times 4 squared. So that's 92 kilogram meters squared. So this is exactly 92.0, 3 significant figures, kilograms times meters squared. All right, fine. This is the total rotational inertia. To get the total rotational kinetic energy, we perform 1/2 the total rotational inertia times the angular velocity squared. Now the angular velocity was given, that's the 2.00 radians per second for the angular velocity. So this is going to be 1/2 times 92.0 kilograms times meters squared times the, I'm running out of room there, but that's 2.00 radians per second squared. All right, so let's perform this calculation for the rotational kinetic energy. So we perform 0.5, that's the same thing as 1/2, times 92 times 2 squared. And 2 squared is 4. 4 times 1/2 should be 2 times 92 should be exactly 184, and that's going to be joules. 184 joules. Now let's see if the units work out. They should. So we have radians per second, we square that. That gives us 1/second squared. Remember, radians in some sense are a unitless quantity. Times kilogram meter squared, you get a kilogram meter squared per second squared, which exactly is a joule. So that's the SI unit of energy. All right, that takes care of part A. Let's now calculate with part B. So with part B, we want to calculate first the linear, that is the tangential speed of each particle. So we need V1, V2, and V3. There's the linear speeds. Now each of these should be the same angular velocity, omega, but each times their respective radius. Radius 1, radius 2, radius 3. Okay, so let's get these values. So we multiply by 2.00 radians per second for each of these linear velocities, because the angular velocity is the same for all the particles, but the radius is different for each particle. It's going to be 3, 2, and 4, respectively, 0.00 meters for the SI unit. So let's get each of these linear velocities. So 2 times 3, so 2 radians per second times 3 meters, that should be 6.00 meters per second. Then we need 2 times 2, that's 4.00 meters per second. And then finally 8.00 meters per second, if my mental math is good. Now, the traditional, that is the linear kinetic energy, should be 1/2 m1 v1 squared plus 1/2 m2 v2 squared plus 1/2 m3 v3 squared. Notice we're just adding the kinetic energy of each particle. By the way, this entire problem we've been ignoring these rigid rods which have negligible mass. We're not worrying about the mass of the rods themselves. We're considering each of these objects like point masses. So I think the 1/2 is common to all the terms, so we can move that out front, and it's going to be mass times velocity squared in each case. So that's going to be 4.00 kilograms times 6.00 meters per second, and we square that. Then we need 2.00 kilograms times the 4.00 meters per second, and we square that, plus finally 3.00 kilograms times the 8.00 meters per second, and we square that. Let's end this parenthesis with the 1/2 on all these terms. So let's get this kinetic energy, the linear kinetic energy. So let's perform 0.5 times parentheses, each mass times each linear velocity squared. So we'll do 4 times 6 squared plus 2 times 4 squared plus 3 times 8 squared. Close the parenthesis. And if I am correct, we should have the same kinetic energy, and it's 184 joules. This is what we expected. So 184 joules. Physics works! Math and science are not broken. So one of the things we find that whether we interpret using rotational kinetic energy or linear kinetic energy, we get the same answer if we consider each point mass having a different moment of inertia and all having the same angular velocity, or having different tangential velocities and different masses, so that we just add up each object's individual linear kinetic energy. Thank you very much for your attention, and I hope you enjoyed this problem and that you learned something. Please smash that like button if you enjoyed this content. Please subscribe to the channel to grow the channel. Please share it amongst your social networks. I want to thank you for watching High Peak Education, and I will see you in the next video.